Hey guys, welcome to the lecture number 3 of Gravitation chapter. And this side Himanshu, and I'm a physics faculty here at askIITians. So I hope you have watched the lecture number 2 and lecture number 1 before you're coming for the lecture number 3. But don't worry if you haven't watched the lecture 1 and 2, because this particular lecture will not have much relation with the lecture 1 and 2. If you have watched it, it will be beneficial for you because you would be able to relate with certain things there. Okay. So what I'm expecting from you that you know at least what is a Newton's law of gravitation. That much at least we should know. Now, this particular session is dedicated about the other models. As I promised with you in the lecture number 1 while doing the introduction that I would not be spending time on the Newton's law of gravitation. I would also discuss with you about few other models, not in very much detail, because Newton's law of gravitation is now everyone is using. Okay. But other models also a little bit idea I'll be giving you. So that's the day today. So today I'll discuss with you about the Kepler's law of models. Kepler's model, right? What he had to say about the solar model. So actually the Kepler has, before Kepler came into the picture in 1609, there were three different solar models available. I'll talk about that also, right? Little bit introduction we'll have about it. But actually, what Kepler was doing, so Kepler was trying to understand the motion of the Mars planet. So everyone is behind the Mars. Elon Musk is also behind the Mars, right? So actually, the Kepler was trying to understand the motion of the planet Mars, and while doing that only, he gave these three models, these three laws, which I am going to discuss with you in today's class. Now, before Kepler, there were three different solar models which were available. If I remember correctly, then one of them was the first model, which was Ptolemy model, right? So Ptolemy assumed that he said actually that Earth is at the center and all the other planets are moving around the Earth. So if I take this as the Earth, right? So assume this as the Earth and Earth is at the center and all the other planets are moving around it like this. So that is what basically the Ptolemy model is. Now the second model. Second model was given by the Copernicus, and what Copernicus had to say, he said that it's basically a heliocentric model. That is also a name. He said that Earth is orbiting the sun, right? Earth is basically orbiting the sun. Now you would think that's true now. That's what we know today also. But wait for some time, right? I'll tell you there was a drawback also. The common drawback in all these three models. And then another guy was his name, if I remember correctly, the Tycho. Yeah. So Tycho said that Earth is at the center again, just like Ptolemy, and Moon and Earth, Sun, they both are orbiting around it. So that's basically the Tycho model. So according to Tycho, the Earth is at the center, and he assumed that Moon and Sun is orbiting around it. In fact, he said that the other planets, they are revolving around the Sun, but Earth is at the center, and Sun is orbiting around the Earth. And what about other planets? They are orbiting around the Sun only. That's what basically the Tycho model is. All right. Now, actually, the main drawback among these three models was that they all have assumed that what is the path of these orbits. They all have said that path of these planets is basically circular, and that was wrong, right? And that was something different in the Kepler's model. So all these three models which I have told you just now, the Ptolemy model, Copernicus model, Tycho model, all these three models had a assumed that the path of these planets is circular, which was completely wrong, right? Path of these planets is not circular, it's something else. So what is that something else? So let me introduce you with the Kepler's law. So let us welcome to the Kepler's law now. Okay, and we'll talk about it. So you can see the beautiful picture there. Okay, in every class you must have seen I come up with some beautiful pictures. All right, so now let us begin with the Kepler's model. Okay. So today's class is dedicated to Kepler's law of motion, and don't worry, not much mathematics would be there. Weight of object on the moon, that also we'll discuss today, right? It's a very simple topic. Already we have done just one thing we need to understand. Okay. Yeah. So let's go ahead. So I guess this picture is showing that somebody have been there, that's why you are here. Right? Somebody have been to the surface, to in the space, to get all these technologies for you. That's why you are riding your car on a road smoothly. I think that's what this picture is indicating. Anyways, nobody knows. It's always about the author, how much he must have thought about it. Let us begin now with the Kepler's law of motion. So there are three Kepler laws, right? First Kepler law says that all the planets moves around the sun. So that's the sun. Just a second. Yeah. So that's the sun. This thing, and this is the planet. It's going so fast. Okay. All the planets are going around their sun in an elliptical orbit. Now this is something new for you guys. What is elliptical? You have heard of circle, right? And that was like an idealistic situation. Like anybody would think of a circular model. Even now, even now, if you ask people who are not from the science background, they would say yes, they all are going in a circle, right? Okay, so actually the path is not circular; it's an elliptical path. Okay, so what do we mean by the elliptical path? So I think now I should take a pause here and I should first go to the ellipse, elliptical geometry. What is that? Don't worry, not much mathematics is gonna come. Very few mathematics. I'll just be telling you. Okay, you can remember it. So let us first of all discuss about the ellipse, right? So what is ellipse basically? It's a flattened circle. It's like an egg shape, right? So if I draw the ellipse, yeah, just a second. So it looks like a flattened circle. Okay, assume it is an ellipse, right? It's like that. Just now I'll show you one picture also, right? So there you will get it very easily. Like you can see in the previous case, yeah, that's one. This green color one. So that's an ellipse. Okay. Now, this is an elliptical path. So how do we get an elliptical path? So before I draw this, let us understand how do we get circle exactly, right? So just think about it. How do we get a circle? So to get a circle, actually, what we do, that suppose you have one fixed point here, okay, and now you have a particle here. If that particle is moving in such a way that its distance from the fixed point remains constant, if a particle moves in such a way that its distance from the fixed point remains constant, it is known as circular path. Okay. Similarly, when we talk about the ellipse, it is something like that. Ellipse is that now we will take the two fixed point, F1 and F2. These two fixed points are basically called the foci of the ellipse, right? F1 and F2. They are not the center of the ellipse, they are focus of the ellipse. And now if the point moves in such a way, that its distance from these two fixed point, this distance is Pf1 and this distance is Pf2. If the sum of these two distances is constant, we call that the particle is going in elliptical orbit. So this point, it should move in this way that its sum of distance from these two fixed point will remain constant. So when this point will come here at this place, again you can measure it. This Pf1, this Pf2. So actually when when Pf1 will decrease, Pf2 will automatically increase. So the resulting trajectory would be like this. Okay, that resembles to the ellipse. Okay, so my drawing is not very good. Okay, so excuse me for that. Anywhere you take the point, suppose if somebody takes a point here at this place, so again you take pf1, you take pf2, sum of these two distances will be again a constant. Suppose this constant is 10, this will remain constant. So when pf1 increases, pf2 decreases, pf2 decreases, pf1 increases. Ultimately the sum would remain constant. So if particle moves in such a way, then this obtained trajectory would be called the elliptical trajectory. I hope you got my point. If you haven't understood, let us do one activity also here. I can show you one video where in this video you will find that this guy would be using a pen. Okay, and there would be two fixed points with the all pins, and from there he will be using a thread. All right, and now he'll move that thread in such a way that the total length of the thread remains constant, right? So the resulting trajectory would be ellipse. So let us have a look on that first of all, then I'll come back here. Okay, so let us first go to that video. So these are the two fixed points, f1 and f2, and now he's gonna keep the thread over there. All right, and now he'll bring a pen. So with that pen he will move in such a way that the thread length will remain constant. So you see this, guys, you see this, right? So when he moved the thread like this, he was getting a trajectory which was an ellipse. Just a second, let me make it slow for you so that you are able to see it. Yeah, see, at any place you see the length of this point from here, length of this point from here will be constant. See, anywhere you take, because the thread length is constant. All right, so that is what is the ellipse, and that's what Kepler had to say. So Kepler said that all these planets also move in this kind of path only around the sun. So that's what the Kepler's first law of motion. All the planets move around the sun in an elliptical orbits, having sun at one of the focus. So if you see that, if you consider that as a Earth, then Earth is going around the sun, right? Okay. Focus one, we have a sun, and focus two, it's empty, nothing is there. Okay. Now there are a few terminologies which are related to the ellipse. I'm going to define that now. I think I should use the previous diagram, that is much better. Okay. So yeah. So let us go back here. Yeah. So you can see this is focus one, and somewhere here we'll have the focus two. Okay. Let me draw a line. Actually, it's not a circle. It's like a flattened circle. If you press it like this, it will become a circle. You should squeeze it like this. It will become a circle. Okay. This is the center of foci f1 and f2, right? So for focus 1 and focus 2, this is the center O. Now here you see this O is the center. So let me call this as a point P and this as a point Q. Oops. This as a point Q. Let's call this as a point R, this as a point S. So actually, I can say that if PO is the midpoint, then simply I can relate that OP will be equal to PQ. And also, this length and this length would be same. As this and this is same, so this O is like a midpoint. So OR will be equal to OS. All right. Now this is which one is the bigger length here? This PQ is bigger or this RS is bigger? Obviously, PQ is bigger. PQ is greater than RS. The length which is bigger, it is known as the major axis. And the length which is smaller, it is known as the minor axis. When you take half, so this entire thing PQ is the major, entire thing RS is the minor. If I talk about half of them, yeah, sorry, this should be OP equals to OQ. Yeah, my mistake. OQ. Okay, now if you talk about half of them, half of PQ. So entire PQ is major and entire RS is minor. So if you take half of PQ, means I'm talking about either OP or I'm talking about either OQ. This is called the semi-major. This is called the semi-major axis. And length of semi-major axis usually we write by A. Similarly, if you take half of RS, so entire RS is a minor axis. If you take half of it, it will be a semi-minor axis. This is represented by A and this is usually represented by B. Simple. I don't think it's going very difficult for you guys. You can easily adopt it. Just like you know for circle, here you are learning it for ellipse. So in ellipse, there are two things: semi-major, semi-minor. Semi-major is represented by the symbol A. Semi-minor is shown by the symbol B. Focus 1, focus 2, right? And all the planets goes in an elliptical orbit around the sun. Now the next part. Okay, by the way, if you make A is equal to B here, what will happen? If you make A is equal to B here, what will happen? It will become a circle. Because now in a circle, all the points will be at the same distance. Any point you pick. Okay, so now let us go for the second part here, right? Which is the Kepler's second law of motion. Now this law is even more interesting. What this law talks about? This law talks about the movement of these orbits of or these planets. Okay, so do not understand the read the statement right now. You'll get confused. First of all, let me explain it. Then we'll read it together. So first of all, let's see that a planet is going in an elliptical orbit this way, clockwise, anti-clockwise. At some instant t1, the planet was at this location. Okay, and at some instant t2, the planet is at this location. Right? So means this planet has covered some certain distance. Right? This planet must have covered some certain distance. So actually what I'm saying that so basically what I'm saying this is basically that the planet is going from T1 to T2 and then it is going from T3 to T4. All right. So actually what will happen that when it goes from T1 to T2, let's say this is the total day taken one day. All right. Now suppose from going from this location to this location, it has taken one day of time. And then in going from T3 to T4, it again has taken one day of time. Okay. So actually, while going from T1 to T2, it is taking one day. And then going back from T3 to T4, it is again taking one day. Got my point? Now actually, if you measure these areas, right? Let's say from T1 to T2, it has taken one day. And from T3 to T4, it has taken one day. Now, if you calculate these areas, this green color area you can see, the area made by this planet at the center, this area. Just a second. Yeah. So this is the one day of time. And now if you calculate this area, I'm talking about the area made by this planet while going from T1 to T2 at this point. Okay. So this is what? This is the total area, let's say A1. And now while this is going from T3 to T4, let's say this area is A2. So what Kepler had to say that every planet covers equal areas in equal times. So if I assume that it's, let's say, uh, 14th of January, right? So 14th of January started from here, t equal to 0, and t equal to 24 hours, means one day is over. So 14th January is done. Now let's say 15th January is starting, okay? Or some other day, let's say we can take some other day, let's say 28th January. So on 28th January, the planet is here. And after 28th January, once, like, this is a t equal to 0 for 28th January, and this is t equal to 24 hour for 28th January. All right. So it's again a one day. So in this one day, this area, if you calculate again, the area covered by the planet, this particular area, this shaded region basically, these two areas will be exactly same. This is what we call the Kepler's second law of motion. Every planet covers equal areas in equal intervals of time, right? So in delta t time, let's say, it will cover delta A area. So in unit time, it will cover an area of delta A by delta t, right? In delta t time, it covers an area of delta A. So in unit time, it will cover an area of delta A by delta t. So that remains constant. The area covered by the planet at the sun per unit time. This remains constant. So just like you say that the distance per unit time is called speed. Similarly, the area per unit time is called aerial velocity. Distance per unit time is called speed. So in a similar way, area per unit time is called aerial velocity. I hope you got my point. Okay. So now let us look at this part now again. So aerial velocity is what? Delta A by delta t. So aerial velocity remains constant. That's also we can understand from here. Okay. So that is what the meaning of Kepler's laws of motion. Second law of motion. Every planet covers equal areas in equal intervals of time. Third law. Third law basically says that when the planet is going in an elliptical orbit, right? So suppose this is elliptical orbit. Let us consider any one of them. Yellow one is okay. So let us consider the yellow one. Okay. So if you talk about the yellow one, so that's a moon here. Let me make it with yellow color. Yeah. Okay. So that's the moon. Now here we can see that this yellow color path is being taken by the planet. Okay. It's moving in this particular way. You look at this yellow color planet. It goes like this. Let me use the pointer. Just a second. Yeah. Now you will be able to see it. See here. It's going this way. All right. It's going this way. So this particular planet is starting from here. It is coming back. It is revolving in the elliptical path and coming back here. So it starts from here and then it comes back here. So basically, it will take a certain amount of time to cover this particular orbit, right? So that time, let's say, is capital T. So what do we call that time? Time taken by a body to complete one revolution, one oscillation. It is called the time period T. So this particular planet, yellow planet, is going like this and this way, and finally it will come back to the same location. So time taken by the planet to go in a particular orbit path to complete one particular orbit is called time period. For example, for Earth, this time period is 365 days, 1 year. After 1 year, it comes back to the same orientation. All right. I'm in the same situation in the plane, orbital plane. So this time square is proportional to, if you see here, this is the moon, so this is the sun, and this will be the Just a second. Let us use a different color. Yeah. So this is the semi-major axis, right? This one, this is the center. So if you talk about the semi-major axis here, so this is the semi-major axis, OQ. OQ is what do we call the semi-major axis, A, right? So basically semi-major axis is OQ. This length, as I told you before, we represent by the symbol A. So time period square, this OQ, basically that is A. So this entire is the major axis, right? So do not get confused here. And this PQ is the major axis and OQ is the semi-major axis, half of major axis. So time period square is proportional to cube of semi-major axis. That's what he had to say about it, the Kepler's third law of motion. All right. So basically, if you look at the Kepler's first law of motion, it talks about the elliptical orbits. If you look at the Kepler's second law of motion, it talks about the aerial velocity remains constant. If you look at the third law of motion, it talks about the time period of the elliptical orbits is proportional to the semi-major axis. Now here we should notice one more thing. Look at the motion of this yellow colored planet. You will find something strange in this animation. What I see here is that this yellow color planet goes very faster when it is closer to the sun. See, suddenly it moves from there. And it moves slowly when it is a bit far away. Similarly, you can see the green color planet. See, it has moved faster and now the green color planet has become slow. And again, it will move faster now. Let's look at the red color planet. How fast it has gone. Right? How fast it has gone. See, suddenly it will cross now. See that. So how fast it was. So basically when the planet is closer to the sun, when the planet is closer to the sun, let us write it here. Planet is closer to the sun. It moves faster. It moves faster. And when it is away from the sun, it moves slower. Now the interesting part is why does it do so? Right? Why it is happening like this? That's what we need to understand. So answer will come from the Kepler's second law of motion. Here you saw that every planet covers equal areas in equal intervals of time. That's pretty good. So if this area is, see, this is a 1 day of time as we have taken here, and this is also 1 day of time. The planet has come from this location to this location in 1 day of time. The planet has come from this location to this location in 1 day of time. Now these two areas are supposed to be equal. Okay, now it's about the common sense. See, if you measure this area, if you measure these areas, then these lengths will when you calculate these lengths, what you will be getting? This length is bigger, right? It is basically called the area of the sector, right? So here this length is bigger, but on this side, if I see this length is very small, okay. So to calculate, to get the same area, I have to spread like this. I'm explaining you in a very simpler way without using any mathematical formula. I can use the formulas also here, half r square theta or something like that, but I will not do that here. Simple, just apply the common sense. When the planet goes from T1 to T2, the length is more. So already the area, the area covered at the sun is automatically more, right? It's a large region. When you talk about from T3 to T4, these lengths are smaller. So if you just take only this much path, then this would be only this much area. But to compensate the area, it covers a larger distance. So when it covers a larger distance, what will happen? its speed will increase because the time is same 1 day. So in the same 1 day of time, it will cover the larger distance now. So you can see here, this path length is more and this path length is very less. Okay, so if I denoted this by d1 and if I denote this by d2, then d2 would be greater than d1. Okay, not very much greater than, I don't know the exact numbers, but it would be greater than d1. That's what I can say theoretically. The reason being because the planet is closer to the sun. So when planet is closer to the sun, obviously what will happen? It will move faster because it has to cover the greater area. When it is away, the greater area is automatically getting covered, right? Because the length is more from there. So that is the consequence of Kepler's second law of motion. It's a very important thing. You should remember it directly. Okay. Now the last topic for the day, and then we will take few questions and then we'll end the class. Weight of the object on moon. So here, first of all, let us understand what is the weight of an object on the earth. Then let's go to the moon. So when I talk about the earth, suppose we have a 2.5 kg object. What is the weight basically? Force exerted by the gravity. That's the weight. Force of gravity. Now, every planet would have a gravity. If I talk about the moon, if I talk about the sun, so if I talk about the earth, everything will have the gravity. Yes, sun would also have, it would also have some mass, right? But nobody would go there. All right. So usually we calculate numerical questions also involve sun, earth, moon, these kind of things, right? Mars. So let us talk about the earth. So suppose you have a 2.5 kg mass. You learnt in the previous lecture that there is something called gravitational field intensity. So which denotes the force acting on a unit mass particle. So right now I'm using a 2.5 kg particle. So total force acting will be how much? 2.5 multiplied 9.8. Approximately we use a 10 also. So when you use 10, you'll get exactly 25 Newton. Approximately if you use this, then you'll be getting around 24 point something. I don't know it exactly, but something like that of would be coming Newtons. So actually, what is the weight? Weight means force of gravity. Now, whether it is a moon surface or it is a Earth surface or it is a Mars surface, you know how to calculate gravity on the surface of a planet. I gave you the formula in the previous lecture. It was gm by r square. Put the mass of that planet, put the radius of that planet, you'll get the answer. When you do this, what you will be getting? You will be getting the answer for the gravity of that on the surface of that planet. To calculate the mass, just put what? Multiply with them there. Mass multiplied gravity is the force, and that is the weight of the object. Now let us talk about weight on the surface of moon. So here you see one thing. Again, that 2.5 kg object, but moon is basically not that heavy as Earth. Moon is 1 by 100 times. Moon is 1 by 100 times smaller in mass than Earth. So if I calculate the gravity on the surface of moon, the formula would be G, but mass would be m over 100. What does it signify? It says that mass of Earth is m. Let us denote it E. G is universal constant, so it would not change. And radius is 1/4 time that of Earth. So I usually write here RE square, but here I have to write R moon square. That is RE by 4 whole square, right? So now what we'll be getting? So mass of the moon is 1 by 100 times and its radius is 1 by 4 times that of Earth. So we will be writing it as GME, GME divided by RE square. In the denominator, this will remain 100 and this 16 will go up, which would come out to be, see, what is this, guys? This is nothing but small g on the surface of Earth. So G moon is equal to G Earth divided by 6 point something. So approximately we can say that gravity on the surface of moon is 1/6 on the surface of Earth. So when I multiply both sides with mass, it will become a weight. So basically what I'll say, that weight on the surface of moon is 1/6 of weight on the surface of Earth. But mass is always same. So if you go to the surface of Moon, the weight machine would be showing you the lesser reading. So don't get scared from it, right? And don't be happy from that. It's not your effort. It's all about the gravity, right? The gravity has done its job there. The gravity has been reduced by 1/6. So now you're getting the weight by reduced by 1/6. So suppose if somebody's weight is 600 Newton, if the mass is 60 kg, then weight would be this. So the same weight machine would show the reading 600 by 6 equal to 100 Newton on the surface of Moon, right? So you can be happy if you go there. So for this 2.5 kg object, you can see the weight has shown the reading 4 Newton, 1/6 of this 4 Newton. All right, 2.5 kg, 2.5 kg. Mass remains same. The weight changes because weight does depend on the gravity. Mass is what? Mass is something which is giving you the idea about the molecules. How many molecules it has. Like suppose if I talk about a wooden block, it is made up of wooden molecules. Whatever is the material. If I talk about plastic, it is made up of plastic, those molecules. Those molecules will remain same whether you're on the surface of Moon or you're on the surface of Earth. So basically weight of the body changes, but mass never changes. Okay, now let us do two questions and then we'll end the class. First question based on the Kepler's law. This is from NEET exam, the medical exam. So here we can see the planet is going in a elliptical orbit about the sun. The shaded area SCD, this one. And another shaded area SAB. These two shaded areas, some relation is given. If I call this as a shaded area A1, and if I call this as a shaded area A2. So what they have said, the shaded area SCD, which is A2, is 2 times the shaded area SAB, A1. Equation number 1. T1 is a time for the planet to move from C to D. Okay, so that is T1. And T2 is a time for the planet to move from C to from A to B. Yeah, exactly. So this time is given as T2. Okay, so T1 is a time for the planet to move from C to D, and T2 is a time for the planet to move from A to B. Correct. This time is T2. Then what is the relation between T1 and T2? That's the question. T1 and T2 relation we have to figure out. Very simple. As I told you, the aerial velocity remains constant. Aerial velocity, area covered per unit time. So if you look at this area, the area is A1, okay, and the time taken is T2. For the different second planet, sorry, this second area, the area is A2 and the time taken is T1. Now basically you can put A2 is equal to 2 times of A1. So I can write this as A1 upon T2 is equal to 2A1 upon T1. Now A1 and A1 will get cancelled out. So this will become T1 equal to 2 times of T2. Please check for any calculation mistake if I have made. So T1 is equal to 2 times of T2. Means this time taken will be twice as that of this time taken. And obviously it has to be because there it is covering SCD, covering double the area. So yes, it should take double the time also so that uniform areas are covered. In equal time, the uniformly equal areas are covered. Let us take one more question. A body of weight 200 Newton on the surface of Earth, how much it will weight half weight down to the center of the Earth? Now that's a tricky question for you guys. It's also again from NEET exam. So how we can solve this question? So as I told you, weight means what? Mass of the body multiplied gravity. That's the weight of the body. So on the surface of Earth, on the surface, it is given as mass multiplied gravity on the surface of Earth, which is equal to 200 newtons. When I talk about d depth below, I have to go down, right? So how much its weight will be when it goes halfway down? Means suppose it's an Earth, and now you have come here, which is halfway down, r by 2. Total is r, so halfway down means r by 2. So how will be writing weight there? Weight at that place, w prime. I'll be writing that as mass is same and gravity of that place. So how do we represent gravity at d depth below? The d value is r by 2 here, basically halfway down. So mass multiplied gravity. Now gravity is how much? You should remember the formula, g multiplied 1 minus d over re. Now here, what is the value of d? D is nothing but re by 2. So 1 minus re by 2 multiplied re. Re will get cancelled out, and this will become mg multiplied 1 minus 1 by 2, which is nothing but half. Mg by 2. What is g here? The weight, gravity on the surface of Earth. This mg is basically weight on the surface of Earth. This value I can put as 200. So w prime will become what? This will become 100 Newton. So that's how we basically get the weight on the surface of at any point inside the surface of the Earth. So that's what about the Kepler laws of motion. I hope you enjoyed the lecture. So today's lecture was not very mathematical. It was a completely theoretical chapter for today's class. And we have learnt about the Kepler laws of motion. In the Kepler laws of motion, there are three laws basically, and we should also remember the Ptolemy contribution, Copernicus contribution, then Tycho's contribution, right? What these people had to say. So you guys should read about them now from different textbook. What these people have done, little bit idea we should have now. And we have also understood the Kepler laws of motion. And in the end, we discussed about the concept of weight. All right. So now here, this is the ending of the chapter basically called gravitation, right? So that's the entire part of gravitation for you guys, right? And now you would be learning the same things in the grade 11 also. So I hope you would remember this lecture now, okay? And the some other concepts would be coming in the grade 11, which is called the gravitational potential and such type of things, which you can do later on, right? Because that will require the concept of integration and all such things. But basic things about the gravitation we have discussed in these classes. All right. So that's all from my side. If any question, just put it on the batch discussion forum. Thank you so much. Enjoy.